In this video, I will try to show you how I calibrated my PT100 for some measurements. And the similar procedure can be applied for calibration of a thermocouple. There is standard protocols for calibrating any temperature sensors like PT100 and thermocouple. Uh, if you follow all these protocols, then you can have accurate calibration. But I did, and due to some reasons, I could not find the accurate temperature readings. There were some errors, like around 1 or 2 Kelvin. So what I did, I measured the four-wire resistance of this PT100 with some other instrument which has already been calibrated with some engineers, someone who calibrated, and then I measured its resistance in same instrument. So I did some readings for temperature versus resistance. The first column stands for uh, temperature, and the second one for its resistance. Okay. Now I will use these readings to uh, make an equation so that which I can use in LabVIEW for other measurement. So I will copy this and paste it in origin. Okay, so the first column is temperature and second one is resistance. Means here we have resistance as function of temperature, but we want opposite of that. We want temperature in function of resistance. So I will do this, copy this one and paste it here and make it as x-axis. So this one is R, yeah, 4-wire resistance readings in ohms, and the second one is temperature in Kelvin, and make plot of it like this. So you can see there is quite smooth variation, quite a linear variation with temperature in this temperature range. Okay, like 50 to 300. Uh, in this range, I want to perform my measurement. So I will fit this data using a second order polynomial. I can increase the polynomial address, but this is enough for this calibration. So I will go with only second order polynomial. So as you can see, fitting is really good for this range. There is a very little variation in low temperature range, but I can ignore it, or if I want to overlap this function in this range also, so I have to increase the order of polynomial. So I will go with this fitting, no problem. So now my work is to feed this equation in LabVIEW. So I will copy this equation and open LabVIEW. And in LabVIEW, I'll open Formula Node and paste the equation here. I will add input as small x and add output as small y. For intercept, I have put some values from here. It is 11.58 something. So I will copy and paste directly here. I will remove the error part, and then again this coefficient b1 should be removed with some numbers. So here it is b1 around 2.60. Again, error part is really low, so it will not affect if I remove them. And this power can be written like this. This is the way of writing powers in LabVIEW. LabVIEW cannot recognize this kind of power. And then I will remove this V2. As you can see, the value of V2 is really low. So this shows that the second order polynomial fitting is good for this case. Okay, and this power thing should be corrected. So it is complete now, and I will put semicolon here and make this variable as control and this one as indicator. So as you can see on front panel, we have two things. This one is input variable, and input variable is resistance in ohms, and the output variable is temperature in Kelvin. So like if we measure resistance 100 ohm, then it will show around 271 Kelvin temperature. So it is quite good. This is actual temperature. So the proper definition of PT100 is its resistance is 100 ohm on 273 Kelvin temperature. But there is error of some 1.9 degree due to some instruments. That's why it is showing something this. And this will be according to the instrument which has already been calibrated. So this will work. So with this method, we can calibrate our in temperature sensor. The same procedure will work for thermocouple. Like in thermocouple, we measure voltage difference and then convert it in temperature. So the voltage gradient can be converted in temperature in the same way like we have converted resistance in temperature.